All right, so let's look at the properties and the theories of both acids and bases. So let's start with the properties of acids. All right, so acids are what we call electrolytes. And that means they are able to conduct. So an electrolyte is a conductor. So strong acids are good conductors. And weak acids are poor conductors. And we're going to look at why in a few minutes. Acids do react with metals to form hydrogen gas. And you'll remember this from our reactions unit. They react with hydroxide compounds to form salt and water, which we call a neutralization reaction. Again, from a review from our reactions unit. All right, and when we say a hydroxide compound, what we're referring to here is a base. All right, so if you wanted to, you could just write base. Just remember that bases are hydroxide. All right, so both of those, however you want to think about it. All right, acids have a sour taste. Why, if you eat a sour candy, is it sour? Because it is acidic. They have a sour taste, and they feel sticky. If you've ever done cooking, all right, maybe you baked a lemon cake, you used a fresh lemon, and you got some lemon juice on your hands. You may have noticed your hands felt sticky after you squeezed out that fresh lemon juice. All right, that is because it is acidic. So, strong acids are going to ionize completely in water. And there are a couple of strong acids that you need to know. Nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid, and hydrochloric acid. These are the strong acids. You need to know these. All right, when we start talking about strong acids and weak acids, I'm going to give you an acid, and I'm going to expect that if I give you one of these, you know it's strong. If it's not one of these, it's weak. So that somebody's going to ask me the question later on, how did you know that was strong? I knew it was strong because I memorized these. All right, these are our strong acids. Please memorize them. All right, weak acids do not ionize completely in water. Okay, so what we're talking about here, when we talk about ionize completely or not completely, we are saying they either go 100% to ions, such as our strong acids. Weak acids form some ions, but not 100% ions. All right, so let's look at our theories. And we're only going to do two theories. There are more than two theories, but these are the two theories that you specifically need to know. All right, and our first theory is an Arrhenius acid. And these theories are named after the scientists who discovered them. All right, and an Arrhenius acid is going to produce hydrogen ions when put in water. So, for example, if we were to look at hydrochloric acid, if it was going to behave as an Arrhenius acid, it would create hydrogen ions and chloride ions. And hydrochloric acid is a strong acid, so it would produce all, it would go to completion. This is going to go to completion. No reactants left. All products which are ions. Bronsted-Lowry acids are what we call proton donors. So, if we were to look at a Bronsted-Lowry acid, for example, HSO4 minus, if we were to put this in water, this hydrogen is going to be donated to water to form a hydronium ion, and I am left with sulfate. If I remove a positive, I become more negative, so SO4 minus is going to become SO4 2 minus. All right, so we have Arrhenius acids which produce hydrogen ions in water when dissolved in water. Bronsted-Lowry are going to donate hydrogen ions. Now, protons are donated one at a time, and we say these are protons, okay, because a hydrogen, if you look at hydrogen on the periodic table, hydrogen has an atomic number of 1. It has 1 proton, all right? Because it is a plus, it has no electrons, so we are simply donating a proton. That's where the name proton donor comes in. So protons are donated one at a time. And this is important, especially when we get to the AP portion of this course. Protons are donated one at a time. We have acids which we call monoprotic. Monoprotic acids have 1 proton. For example, hydrochloric acid. All right, hydrochloric acid has 1 hydrogen, therefore 1 proton, and hydrochloric acid also has the ability to act as a Bronsted-Lowry to donate this hydrogen to water to form a hydronium ion and chloride ions. We have diprotic acids, di meaning 2, so 2 protons. And an example of this would be sulfuric acid. It does have 2 hydrogens, so 2 protons. Now we are going to donate these one at a time. So when 1 proton donates to form a hydronium ion, I am left with H, because I'm only getting rid of 1 hydrogen, SO4, and if I get rid of a positive, I become negative. So here's where this HSO4 came in my Bronsted-Lowry example. All right, it was the first donation of a proton from sulfuric acid. Now there is still a proton that can be donated. So I can do a second step where HSO4 donates its proton to form H3O+. And this becomes sulfate, SO4 2 minus. Finally, we have triprotic acids. Tri meaning 3. So that is 3 protons. And an example of this would be phosphoric acid. Phosphoric acid does have 3 protons. So we're going to donate these one at a time. So if we have 3 protons, we're going to have 3 steps. So my first step, we donate a hydrogen to form a hydronium ion. And I am left with 2 hydrogens plus PO4 within it. And since I got rid of a positive, I become negative. Now this H2PO4 minus can undergo another donation where I'm going to donate a hydrogen. So I'm going to form hydronium ions. I get rid of a hydrogen, so now I only have one. PO4 is still there. I got rid of a positive, so that becomes a -2. And now I still have a proton that can be donated. So my third step here is to get rid of this final hydrogen to form hydronium again. And this PO4 is now going to become, instead of 2-, I got rid of a positive, so it's going to become 3-, which is our phosphate.